Welcome back everyone. Let's talk about internal heat gain. We have internal heat gain due to presence of human inside, machine and equipment inside, pressure. Also, if there is any other uh, pipeline going through the room, there will be an internal heat incurred inside the room. So firstly, we are going to take care of the sensible heat for now, and we're going to find out load due to the occupants, lighting, equipment appliance, and others. Okay, starting with human. For now, we know we have how many people inside. Let's consider two people. Yeah, 4 person is inside the facility. So, the 4 person inside the facility, and they are doing heavy work as per the information we have from the data sheet. Let me find out the data sheet. Yeah. 4 person heavy industrial work. So for this person, there will be heat incurred, sensible and latent heat will be introduced in the facility. Okay, so here is the table 48. It talks about heat gain from people. The very first column we get activity, degree of activity column. Here is activity like seated rest, seated and very light work, office work, seated walking slowly, walking seated, seated walking slowly, seated sedentary, light bench work, moderate dancing, walking, heavy work like this one. And typical application examples are in here, like for example, seated rest got theater, standing, walking slowly like in the bank, sedentary work like in the restaurant, heavy work like in the factory. Okay. And then we need to know the room dry bulb temperature inside. So we know what is the amount of sensible and latent heat inside. Total heat will be the same actually. For instance, if the temperature is 70°F for each person, you're going to get 605 BTU of sensible heat and 845 BTU of latent heat. In this particular segment, we are considering only sensible heat 605. Now let's go back and take a note in here. 605. And there are 4 people inside. Multiply with the 4, we get total 605 into 4. 2420 BTU. 2420 BTU for the human inside. For lighting, as we know, there are 200 watts of light. So 200, and from the formula 3.4, total amount of heat incurred by lighting is 200 into 3.4, 680 watts. Appliance and equipment. In this particular note, we have provided heat load due to various types of appliances, which includes but not limited to not electric equipments, and then we have steam heated equipments, then we have hair dryer likes equipments, okay, gas burning equipments, everything is in here. If you don't have find your particular data, you can look at ASHRAE or from the manufacturer's data sheet. For instance, we have a coffee brewer. Let's say this coffee brewer, we get sensible heat 900 BTU per hour and latent heat 220 BTU per hour, and total 1120 BTU per hour. So for now, let's consider from the coffee brewer that we are having inside is 900 BTU per hour. Let me write it down here. The coffee brewer has 900 BTU per hour. There are other equipments Like there are 2 horsepower motor, hot surface 5 feet, and we have 5 5 square feet actually, and hot water pipe 2 inch for 10 feet. Let's calculate them. For firstly, machine 2 horsepower motor we have. So you can get this data from which table? Mm, Not this one. This is the data. Table 53. Wait a bit. I think. Yeah, that's better. If you come to the very first column, we get horsepower. So 2 horsepower is the motor rating, is 80% running. Now, if the motor is inside and driving machine inside, the amount of energy produced here is 6,380 BTU. If motor outside but machine inside the room is 5,100 BTU, and if motor inside the room and machine is outside the room is 180 BTU. In most scenarios, we have motor and machine inside, so we'll consider 6,380 BTU for 2 horsepower of motor. 6,380. Let me write it down here for motor 6,380 BTU per hour. Okay, then again we have hot surface 5 square feet for hot surface. Let's go to the table relevant to hot surface. It should be at the bottom, I guess. Okay. Yeah, this one. So this is table number 57. This is about heat transmission coefficient for Fanda for uninsulated tanks. And the unit is BTU per hour per square feet per degree Fahrenheit of temperature difference. So for instance, the construction, it can be metal, wood, or concrete. The hot surface, let's see of a machine. If it is made by wood, you consider this. If it's concrete, you consider this. If your machine is made by metal, which is usually made by metal, you can consider this. And then is it painted or bright nickel? Let's say the machine is bright nickel. Then you have to find the temperature difference of the room and the surface. Let's say if the surface temperature is 100 degree Fahrenheit and room temperature is 70 degree Fahrenheit, you take difference 30 degree Fahrenheit. And let's say if surface temperature is 120 degree Fahrenheit and room temperature 70 degree Fahrenheit, in that case we have temperature difference of 50 degree Fahrenheit. Now if you come in here in the table, is the line 50 degree Fahrenheit, 100, 150, 1 and 200 degree Fahrenheit difference. Okay, now where is the hot surface? Let's say this is the machine. If the hot surface is on the top of the machine, then you use the data for the top here. If the hot surface on the side of the machine, you use the data here, the vertical, this one. And if hot surface at the bottom of the machine, you use this data. So let's say our hot surface is on the side. In that case, it's 1.3 BTU. The unit is BTU per hour per square feet per degree Fahrenheit after temperature difference. So for now we know it's 1.3. Then BTU per hour per square feet. What is the size? I think it is 5 square feet. Multiply with temperature difference is 50. Then you can get the whole idea about the temperature or heat incurred due to hot surface. Let me go back and put it on the note. So hot surface 5 square feet multiply with 1.3 from the table and multiply with the temperature difference 50. So let's calculate how much. 1.3 into 5 into 50. Not much, it's only 325 BTU. Then again, there is a hot water pipe running through the facility. It's 2 inch in size and 10 feet. Hmm. Let me take you to the table relevant to this. Electrical motor we have already done. Now this one. Heat transfer transmission coefficient for bare steel pipe. If your steel pipe is bare, non-insulated, use this one. Heat transfer coefficient for insulated pipe. If your pipe is insulated, use this table. So very simple. So for instance, let's consider pipe with insulation in our discussion. Okay. Heat transmission coefficient for insulated pipes, BTU per hour per linear feet per degree Fahrenheit. So here is the pipe size 2 inch. If it has insulation 1 inch in thickness, and then you have 0.3 coefficient. So 0.3 multiply with linear feet. The pipe is 10 feet in length. Multiply with degree Fahrenheit temperature difference of pipe and room. Let's say the temperature inside the pipe is 120. In that case, 120 minus 70, we have 50. So total heat incurred is, let's calculate, into 10 into 50 is 150 BTU per BTU per hour. So let's put it down in here, 0.3 into 10 into 50. Zero point 0.3 into 10 into 120 minus 70. What we get is 150 BTU. Okay, so for the light, we have 680 BTU, and for machine, we have motor 6380 BTU, 6380 BTU. Let's put this data on E20 sheet. Here is our E20 sheet. Until now, we have done slot transmission gain except walls and roof. Infiltration has not been done yet. We'll do it later on. For people, let's do this one, internal heat gain. Per people, we have 4 per person inside, and per person is 605. 605. So total, we have 2420. Lighting is let's directly put it in watt. 200. Uh, Actually, you can do it by like watt per square feet, like 100 square feet, and every square feet is 2 watt, 683. And equipment, let's put it directly. Equipment, we have coffee machine, coffee machine. It's 900 BTU, as we have done earlier. 900 BTU. And for motor, we have 6,300. Let me check it back. 6,380. And let's put it directly here. What else we have in our calculation? We have hot pipe. So for the pipe, let's put the pipe here. How much you got for the pipe? Okay, the hot pipe 0.3 multiplied by 10 multiplied by 50. So pipe 0.3 multiplied by 10, 50, 10. And then we have hot surface. For hot surface, what you got is 1.3 BTU per hour per square feet per degree Fahrenheit. So you're going to use that in here, 1.3. Mm. Temperature difference is again 50. Fahrenheit. And then we have the area is 5 square feet. So now if we multiply, it's the amount of heat incurred from hot surface. I think that's all. Let me check it back. We have considered motor, lighting, everything. Yeah, I think we are done. Okay, that's it. By now, we have calculated internal heat gain. Uh, let's move on. We are going to talk about infiltration and outside air. And after that, we will go for effective room sensible heat, this one, and effective uh, room latent heat. Okay, let's move forward. I guess we have done most of the work here. By now, we already know heat incurred from various sources relevant to occupants, lighting, appliance from the table, and cooking, miscellaneous equipment, yeah, pipe, hot surface, hot pipe, everything. I think you are quite ready for any industrial project by now. Okay, let's move on.